Today we are going to do section 9.2 first. Let's look at the book. We have that. This page is already scanned, should be, but we'll just do this again quickly. And let's see, is my camera focusing? Good enough. And then the bottom. Okay, that's that. Next, 290 and 291. That is, I think, yes. All right. That's the whole page. And then a little closer on the top. And then a bit closer on the bottom. Let's see. This side seems to be less focused. Yeah. Okay, that looks a little better. Okay, so that's that. So let's start on page 288, the convergence test. First, let's talk about the ratio test. It's the same ratio test we had in basic calculus, but we're going to give it a somewhat more rigorous proof and talk about certain details. So the ratio test, right now we're only thinking about things that are positive. So let's say UK is bigger than 0. And then the limit of UK plus 1 over UK is equal to L, and L is less than 1. Okay, and so this is very, very clear. We know what we're talking about. If that is the case, then the series is convergent. On the other hand, if L is bigger than 1, and it could be infinity, then the limit will go to infinity. If L equals to 1, then the test fails. Okay, we don't know. It could go either way. So then let's prove the case where L is less than 1 first. If L is less than 1, then we can pick a number for R between L and 1. Well, given any number between L and 1, that UK plus 1 over UK would be less than R. If the number k is big enough, because the limit is because the limit is equal to L, then if you get close enough, then it will be the limit will be less than R, which is slightly bigger than L, right? And then so the k is close enough if k is bigger than m, but the m it will be dependent on R. But as long as we just to choose m that's big enough, then the entire tail end of the series works out, satisfy the condition of being less than R. Some of the initial terms might not satisfy, but when it comes to series, we don't care about the initial terms when it comes to proving divergence or convergence, because the initial terms, no matter how many there are always it's just a finite number. And it doesn't affect convergence or divergence. The series either converge or diverge, no matter what the first million terms or first billion terms are. Okay, it changes nothing. We only care about the tail end when it comes to proving convergence or divergence. So at that point, then m is we have now that UK plus 1 over UK is less than R. We can then pull out a chain like this. Let's see, right here. Okay, I have it written down here. The book skipped this writing. What happens is if UK plus 1 over UK is less than R, then of course UK plus 1 is less than R times UK. And then the next step is, let's consider U of m plus p. Okay, so there's a whole bunch of them. And that would be less than R times U m plus p minus 1, the one that's right before it, right? And then this one is going to be less than m plus p minus 2 multiplied by R. So we have 2 R's being multiplied. And if you keep going, eventually we go down to um, then you have R to the power p. That is how this thing is worked out. Okay, so then eventually we got, so that's how we got to this point where um plus p is is less than r to the power p times um, and then at this point, then we can let's see. Then we use this is the geometric series, right? Let's see, what is T1? Okay, so T1 is right on page 285. So based on T1, this series then converges. Okay, so if this thing converges, then the one we have right now is just a matter of factoring out um. So each one is bounded by the um, where m is a fixed large number. And therefore the series then is bounded by um, one of the fixed numbers, times the sum of r to the power p, which is the geometric series, which converges. And therefore this, so we have proven that the convergence if L is less than 1. Next, if L is bigger than 1, or especially if L is infinity, then the ratio is greater than 1, which means each UK is, that means each UK is going to be bigger than um, which is bigger than 0. That's since every single UK is given as bigger than 0. Okay, and so therefore the limit of this, the terms don't even go to 0, then it diverges, because the least we can do in a infinite series is the limit of the terms had better go to 0. Now, so this is for strictly, theorem 4 is for strictly positive ratio, because it has to be strictly positive, because each term has to go under the division line and be the denominator. So we can't allow it to be 0. But if there are a certain number of zeros that's distributed in there, that changes nothing, because 0 just, we can just throw those away. And so that even if you have zeros in there, you can turn that series by throwing away the zeros and turn it into a new series which add up to be the same thing, but without zeros in it. Okay, so let's look at the next page. We have what happens when L equal to 1. L equal to 1 means we don't know. Okay, you can go either way. As an example, the harmonic series would give you L equals to 1, as the limit of UK plus 1 over UK is equal to 1, and the harmonic series go to infinity, whereas 1 over k squared, as we know from previous lesson, is convergent, even though the limit is also 1. Okay, that is if you were to do it. So that's that. Next, let's consider the root test. Now, the root test is something again familiar from basic calculus. Where the root test states that if UK is bigger than 0, and then the limit as k goes to infinity of the root of UK, so that's a new sequence. If this sequence equals to, the limit goes to L, and the limit equals L, the limit equals L, and L is less than 1, and then this sequence is convergent. On the other hand, if L is bigger than 1, and maybe even go up to infinity, and then the sequence also diverges. If L equals to 1, then we can't do anything about it. Now, the proof of this thing goes similarly to the previous theorem. Okay, theorem 4 and theorem 5 happens to be proven in almost identical ways, so we're going to skip the proof. And the point is, you just you come up with something, and then some kind of geometric series or something. But being that the book doesn't want to talk about it, I also don't feel like it. So let's move on to theorem 6, which is the integral test. The integral test, now the root test is not that useful, because the only time you need it is when your expression actually has the kth power in there, so that you can take the kth root. Most of the time, why would you take a kth root out of no reason? So you wouldn't be doing that. The ratio test is somewhat more useful, okay, but although it's still limited, because A lot of times the L equals to 1, so then you don't know. So you did it for nothing. And then the integral test, however, works much better, although it is also harder to use because you have to take the integral of something. And the integral of something might not be easy to take, okay? And so even with your calculator, I mean, even with the integral calculator, that might be a real pain. So then, but anyway, it is the most powerful one because it has no exceptions. There's no such thing as if something equals to 1, it doesn't work. It works on all conditions. So let's look at the integral test, Theorem 6, which states that, let's say f of x is a positive function. It could be 0, okay? But however, it is also decreasing. Or put it another way, it is non-increasing. And remember this symbol, the down arrow from previous days, a few chapters ago. Okay, that means non-increasing. And so the limit from 1 to infinity, they write it this way to be fully legal, okay? But we'll just call it limit integral from 1 to infinity is what this means. From 1 to infinity of f of x is equal to a, or it equals to some fixed number a. That would mean that the series is convergent. Now, if a equals to infinity, that would mean that a is divergent. So as you notice, there is no 1 to worry about here. This is clear cut, okay? Either equals to a or equals to infinity. There is no other option because f is bigger than or equal to 0, okay? It's gonna add, when you're adding a bunch of infinite positive stuff, you better be either finite or infinite. There's no other option. And then the book also mentioned this part, that if f is belong to C1, which most of our, if not all of our homework is going to be that way, okay, we'll have f that's at least C1, then f of x decreasing is the same as saying f prime is less than or equal to 0 during the entire area. Okay, and that is from 1 to infinity, f prime is less than or equal to 0. So in the homework, now this statement is not necessary in the proof, but this statement is written here so that you know that in the homework, to satisfy the condition fx is decreasing, you just have to show that f prime of x is less than or equal to 0. Then that's sufficient to satisfy hypothesis 1. So anyway, let's move on. Now by hypothesis 1, then f of k plus 1 is going to be less than f of k, being that f is decreasing. Okay, so f of k plus 1 is less than f of x, which is less than f of k. And then next step we're going to do is integrate both terms. The integration then gives it just end up being that these two are actually constants with respect to x. The integration, we get this thing back because we're integrating from k to k plus 1. So we get this thing back here and here, and just stuck the integral sign in there. So we got this far. And this is true for each k. So k is held constant in this case. And the k is going from 1 to n. Well, however many k's, however many of the, we have a top limit here. So for these limited amount of k, the integral situation happens. And then the next thing we're going to do is we're going to slap on the well, we're going to add them all up, okay? The left side and the right side shall be all added up accordingly from such that we're adding it from, originally we're going each one going from k to k plus 1. If you add it from k equal to 1 to k equal to 2, and so on, so eventually this situation is true. Now, please stare at this closely until you make sure that all the indexes work out, okay? So, because this part start counting at k equal to 1, whereas that part start counting at k equal to 2, and it ends at n plus 1. And then the integral integrates from 1 to n plus 1. So those are some of the details that you need to take some time to make sure it all works out. And that way, we add up all these inequalities. So now we go to the next step. Now, so the next thing we consider is if hypothesis 2 equals to the number a, and then that is the integral of from 1 to r of fx dx equal to a. If this is assuming this hypothesis stands, then we let n go to infinity in this integration, okay, and then we get this situation, just this inequality here. We get this thing is less than or equal to a plus f of 1. And that's because we're starting count here. Here we're starting count at k equal to 2. If we're going to start count at k equal to 1, so we need to add f1 on the other side to be fair. So we got to this point. So next. And as a result of that, then on the next page, page 290, I should write it down. Now, I should say that before we get to the next page, look at this again. As you can see, that being that this is true for any n, okay, this side is a fixed numbers. So being that this is true for any n, we can let n go to infinity and come to our conclusion that the series, let's look at the next page, okay, where n did go to infinity, that then the series is bounded by a finite number, and therefore the series is convergent. So we proved convergence in that case. Now, what if a is infinity? Now, if a is infinity, then we are going to use the other side, okay? Let's say that this, in other words, what if this integral equals infinity? Then we're going to use this thing, which means that this thing is bigger than infinity. Now, look at how neat that is. It's all a matter of the integral is bounded by two things that look very similar, right? It's a cute trick. So I mean, but anyway, so if a is infinity, that is the integral is infinity, we'll use this part of the inequality, okay? And then so then that means the series is bigger than infinity on the finite side. Let's see, what am I doing here? Okay, so this series the series of is bigger than infinity. Actually, let's look at the previous page again. So if we use this one, with this integral being infinity, this thing up to n is bigger than or equal to infinity. So if we let it go to infinity, it's still bigger than or equal to infinity, which means it goes to infinity, which means it diverges, as is said on the previous page, right here. Okay, so then we got the infinity part that taken care of. So observe that there is no case in which the test fails. Now and then the limit in hypothesis, give me a second here, what? Now the limit of the integral has to exist because everything's positive, okay? So either it's a finite number or it's infinite, there's no other option. So and now let's consider the next, so now that we're done with proving that thing, we are gonna look at something else, okay? So next, we are going to consider the test series T2, which is done a few pages ago, 286. Okay, here's the series T2, where we have, and is this thing, the test series has different conditions, I guess. If it's a p bigger than 0 and it converges, and p less than 0, then it diverges. Not 0, 1. But anyway, the details, and we can now use a newfound theorem to prove that all that works. So, but that's a bit tedious. So please do this yourself, okay? And it goes all the way here, as. So please work through that the same way that I believe I also did it right here. If you have any questions, it's just a bunch of details and you have to do some basic integration, that sort of thing. And then pay attention if p is bigger than 1 and less than 1. That always gives me a headache. But and messing with stuff that's bigger than 1, less than 1, is a positive, is a negative. But anyway, so please do that. And let's then move on to the next sentence, where we'll now consider test series T3, which is the sum of k goes from 2 to infinity of k log k to the power p. All right. So then again, we will apply our brand new integral test, and that comes up with something for p bigger than 0, and then for p less than 0. And so please do that yourself as well. Okay. Let me see. I guess I did that here too. What I just showed you includes the test T3. Here's the part of T3 and certain integration details. So please do that. Go over that yourself. Okay, make sure everything works out, and then we'll look at the next thing, which is corollary 6. Corollary 6 will be needed in the homework. And so don't forget to use corollary 6 in the homework. I also have certain. Let's see, did I forget something? Let me check. Oh, I forgot to show you that this for the test series T2, which is something we did just a little while ago. That is this one. Okay, for this one, where the test series of f of x equal to x to the power minus p. Is that T2? Actually, why don't I show you T2 again? Where is it? Here it is. Okay, so here's T2 on a few pages ago. Now T2 is this thing. Now this thing is the integral test applies to this thing no matter what p value is. And I plotted a graph just to show you that fact. That is, here's the graph, okay? Now, it's not strictly speaking necessary, but it's good to look at it. Look at that. So here's the different values of p. When p is 0.1, the red line, as you can see, it still goes to 0, but very slowly. Whereas p equals to 2, that's the purple line at the bottom. See, that goes to 0 very fast. So that's the series then converges. Whereas when it's less than 1, well, at 1, the series already diverges, because that's a harmonic series. But anymore, it all diverges. However, it's still going to 0 though. It just goes to 0 much slower is all. But it does go to 0. And I just want to show you that point, okay? And that's that. So next, we have corollary 6. Let's get back to corollary 6 on this page, where corollary 6, we pull back the old formula from the previous page. That is, let's see, where's A? Well, anyway, so from the theorem 6, we got the two inequalities. The first one is on the top of the page, where the sum and the infinite sum, the series is less than or equal to a plus f of 1, right, which is given down here. This part of the inequality, the series less than a plus f of 1. And then what is the series bigger than? The series is also bigger than or equal to a if on the other side, okay, that is, if this, on the previous page, if the integral goes to a, then the series is also bigger than or equal to a if you let n go to infinity. So as a result, the integral then is bounded by those two values. The series is bounded between, is bigger than a, and then it's less than a plus f of 1. So that is where it's controlled. Those two values may or may not be close to each other depending on what f1 is. And so next, we can then establish some kind of a bound as a result of this, for a series. For example, then what is this? This is zeta p. That zeta is isn't zeta t2? Yeah, that's this thing, which is that well, doesn't matter what it is, okay? But anyway, here's T2, and so with T2, then right here, for T2, then we can establish this kind of calculation. Once you calculate what A is, if you take the integral, then follow this formula and take A. A is the integral, right? The result of the integral. So if you take the integral, then you come up with this solution. So please do that yourself, as I believe I've done it. Let's see, yeah, actually it's still on the same page. I guess it's at the very bottom. Whereas as zeta p, you take the integration and equals 1 over p minus 1. So then this thing equals to that. Okay, so please do that yourself, and so that I don't have to explain that. And more importantly, being that all the terms of the series are finite, if p is bigger than 1, the sum is greater than its first term. So then it is also true that this value might be this value, over here. So it is also true that this theta p is bigger than or equal to 1 because its first term, the series first term is 1. So that also stands. And what's more, we noticed something interesting. That is, first, the zeta p is, let me think, is that? Okay, remember, this is zeta p. Okay, let's not, so this is zeta p, which is 1 over the sum of 1 over k to the power p, and it has these interesting qualities. First, from this inequality, we know that as p goes to infinity, then this thing is squeezed. If p is going to infinity, top and bottom there, then this fraction becomes 1. So then zeta p tends to 1 if p becomes infinite. As p gets bigger and bigger, zeta p the infinite series will become 1. On the other hand, based on the previous formula, if p is approaching 1, okay, instead of infinity, it's approaching 1, then both this fraction and that fraction goes to infinity, right? If it's going to 1. And then, so then that forces the zeta p to go to infinity if p approaches 1. So that is, so we can, as a result, estimate what is zeta p that way. All right, so that is the end of this section. It's a pretty short section, right? And let's do some homework. For homework, let me get the homework ready. So for homework, please do on page 291, please do problems 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 14. And when you're done, let's talk about them. Oh, I forgot to show you the hints. Let me see, I should write it down first. I prepared a bunch of hints because trying different tests is a complete waste of time, basically. So if you like, please use these hints, okay? If you feel like it, but of course, feel free to try it yourself before you look at the hints. So here are the hints for various problems. Okay, I guess that's that. Another thing I need to mention is problem 11. The problem is wrong. It says something about 1/4 here. Let me show you the book. That is right. Where is it? Problem 11. Yeah, the problem 11 says right here that this thing is less than pi over 4 plus 1/4. That is not correct. Okay, this should be 1/2. And you will see it when you do the homework, and I'll talk about it later when I get to problem 11. So for now, let's talk about the homework after you finish it. So let's look at homework problem 1. The problems are pretty much just a matter of doing something, I guess. There's not particularly exciting once you know which test to use. Okay, here's problem 1, and then 2, and then for problem 1, I try to use the ratio test, but it doesn't work. Okay, we have to use pull this other trick. Well, don't have to. There's more than one way to skin the cat, but that's what I did, and it seems to work. And then problem 3, we have this is. What was problem 3? I think you're supposed to, use the integral test, and that comes out nicely. And that, yes, if p is, well, whatever. Just use the integral test. And the integration is, well, I just use a calculator to do the integration. I'm about worn out doing, trying different tests, which is, well, I think this one I used the L'Hopital's rule for problem 3. Problem 4, again, use the integral test, and this thing is turns out to be not as hard to integrate as it looks. Okay, the integral is just that, but anyway, if you use the integral test, then everything should come out okay after you work out the details. And then problem 5 is just a root test, and that's much faster to do. That's a one-liner. Okay. So next, let's start with problem 6. But before that, I want to point out that the hint that I show you for problem 8 is wrong. Okay, I typed it in here. I didn't pay much attention. It's bigger than 1 over 2x. The x should not be in the denominator. The x is in the numerator. I should have moved it over, but I didn't push the move over button, and therefore now x is stuck down here, and that's wrong. That is the hint is actually reads arctan of x is bigger than 1/2 x. Like where is it? Right here. See, here is that's the hint. And in case you're wondering, I got this hint from Google. I wasn't, because I was getting really tired of messing around digging for which proof works. It's better if we just know which proof works and let's get on with it. Okay, so that's how I'm going to do, and well, that's how I did all the problems. Anyway, so problem 6 is the hint is once you have the hint. Well, for all these things, when they need hints, once you have the hint, here's a hint, and then everything just falls out right away. And then, so the next thing is the same way. Problem 7, was there a hint there? Maybe not. And so problem 8, problem 8 has a major hint, which is this situation is true. And you can prove it by plotting both graphs in decimals. And being that we're only counting from 0 to x to 1, we can know beyond a doubt that this is bigger than that. Okay? Because we're only looking at from 0 to 1. And then everything else will come out nicely. And then problem 9 is, well, I don't think problem 9 needs a hint. It diverges or something. Which one was, well, whatever. I think problem 7, the terms don't even go to 0. So that's, and that one is, well, I don't know what that one is. Anyway, so that one diverges. Let's see, what was the hint for problem 7? And yeah, the hint for problem 7 is just that it diverges. So there's no need for us to wear ourselves out doing nonsense. And then so that's problem 9, which diverges. And I don't think problem 9 has a hint. It's pretty, you just go about the regular way of doing things or something. And then problem 10, yeah, problem 10 also has a hint, which is I think this thing right here. Right? What was the hint for problem 10? Yeah, it's k bigger than natural log of k to the power n, regardless of what n is. Now that to prove that, we can just calculate the limit of the ratio, and which might require L'Hopital's rule several times, and then as a result, we can prove everything. So that's that. So next, let's look at problem 11. Next, let's consider problem 11. Problem 11 is easy to do if you just follow the hint, which is use corollary 6. Now, the problem with problem 11 is after I was done with it, I couldn't get the answer. It says less than pi over 4. But if you plug into corollary 6, you're going to get not pi over 4, but pi over 2. No, I don't mean pi over 4. I mean 1/4. Okay, where f1 equals to 1/2, and I mean if you calculate it. So then so I don't know where they got the quarter, and then what I did is I Googled this thing. Okay, and the Google says that is not true. There is no way that this series that's the original series is less than this thing. Okay, it's mathematically incorrect. That's the most politically correct way of saying that. So anyway, that is, I mean, what other way is there to be incorrect? I mean, mathematically is the only way we know of, right? So anyway, so please change this problem to the 1/4 is wrong. It should be 1/2, okay? Because that's what you calculate. If you plug in k equal to 1, that's 1/2, and also that's what Google says. So it must be true. So that is problem 11. Problem 12 is a matter of doing grunt work. Okay, we have to do this thing 3 ways, which is okay. Let's do so. And well, all three ways don't take very much. So here's all three ways here, I think. No, that's, yeah, theorem 4, theorem 5, theorem 6. And that is, that's that. Next, let's look at problem 14, which is right here. All right, problem 14, and we again apply corollary 6. And then we, by calculating what A is. And so that comes out pretty good. But the question is, well, we have to confirm it. Yeah, I really don't feel like confirming nothing. So I plotted it into the calculator or something, all these things, and they turn out to be 3 graphs that looks like that, okay, just like the way it should. And that should be good enough for anybody. So that concludes this section.